Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering. Silicon single crystal wafer is the starting base material for manufacture of an ASIC. Semiconductor process steps involve repeated cycles of photolithography, etching, doping, deposition, and planarization are used to create complex CMOS gate structure. Base layer create devices, and insulated metal layers create interconnects, and the combination of them builds an ASIC structure. In this video, we will review a simplified CMOS inverter gate manufacturing process that creates the basic building block of digital electronics. On the substrate, two heavily doped source and drain islands, separated by a region known as channel, is created. A thin silicon dioxide, coated with a polysilicon layer, is placed over channel area that forms the gate. The combination of source, drain, channel, and gate forms a MOS transistor. Silicon dioxide sandwiched between the polysilicon and the substrate forms an FET gate capacitor. The capacitive input makes it a voltage-operated device and finds wide range of analog and digital applications. There are several CMOS logic gates fabrication technologies, of which the self-aligned gate process creates an improved features. In this process, MOS transistor fabrication does not rely on manual layer alignment processing. Instead, using already created gate layer is aligned and creates source and drain layers. This technique minimizes the layer overlap mismatch, reduces the device parasitic capacitances, and improves the speed and performance. Semiconductor device fabrication starts with growing a predefined resistivity and orientation silicon single crystal that is sliced into wafers of required thickness. On the wafers, using physical masks and semiconductor processes create various patterned material layers. The overlapping active and interconnecting layer structure realizes the required functionality. Processed wafers are then tested, sorted, scribed, mounted and packaged to create a finished ASIC. The choice of substrate material is critical for achieving optimal ASIC performance. Highly purified P-type or N-type doped silicon single crystals with predefined parameters such as thickness, diameter, resistivity, and orientation are used as the starting material. In CMOS technology, both NMOS and PMOS transistors are fabricated on a common substrate. This is achieved by creating an artificial well within the substrate, where one type of transistor is mounted in the well and the other on the substrate. CMOS process employs local oxidation of silicon, that is popularly known as LOCOS. In this process, the transistors are fabricated on a common substrate and are isolated by creating a field oxide layer. Isolating layer minimizes the transistor's electrical signal interference and improves logic gate performance. The active region, reserved for the fabrication of transistors, lies between the field oxide layers. This region accommodates source, drain and predefined channel area and eliminates the possibility of creating a short channel device. Initially, a thin layer of silicon dioxide is deposited, over which another layer of silicon nitride is grown. Using photolithography and oxidation process, the oxide thickness is further increased to create a thick field oxide layer. The field oxide isolates transistors and the silicon nitride acts as a barrier layer that protects the active region. Various other isolation techniques employed are shallow trench isolation, twin well processes, etc. Active region locations are identified by created oxide barrier layers. In this region, MOS transistor, consisting of source, drain implants, and thin gate oxide layers, are to be created. The channel area is situated between the source and drain regions and lies directly beneath the gate oxide layer. The channel length and the width, that is the channel area, underneath the gate is critical in realizing the required performance parameters. Gate voltage dumps and controls the channel charges that result in drain current. Ensuring channel area minimizes the probability of creating a short channel device and avoid occurrence of short channel effects. In CMOS technology, an artificial substrate called a well is created within the substrate. One of the transistor is mounted in well and the other in the substrate. The well, being smaller in size, will have limited free carriers, and hence the device mounted in the well exhibits inferior performance. The CMOS logic gate has a built-in parasitic PNPN switch structure. This makes it susceptible to latch-up phenomenon that leads to the gate burnout in short circuit. An N-type well is created by implanting phosphorus-like dopant into the mask-identified well areas. By controlling well doping level, the transistor threshold is controlled. A metal gate, an oxide layer, and a semiconductor substrate forms a gate capacitor of CMOS device. Due to better thermal compatibility of polysilicon with silicon dioxide layers, the metal contact layer has been replaced by polysilicon. A thin oxide layer acts as dielectric material, and poly along with substrate form two plates of the capacitor. The oxide thickness plays a major role and determines gate breakdown voltage, capacitance, and transistor threshold voltage. The CMOS gate voltage operates the capacitor in accumulation, depletion, and inversion and varies the capacitance. In the active region, a thermal oxidation process, thin silicon dioxide layer is grown, and over it, using chemical vapor deposition process, a thin layer of polysilicon is created. The polysilicon layer is used as mask in creating source drain layers. Source and drain are heavily doped regions that are created in the substrate. The gate voltage creates accumulation, inversion, and saturation modes of channel operation and modulates conductivity. Source emits the carriers that passes through channel and is collected by the drain. For efficient creation of source carriers, the source and drain regions are heavily doped. The MOSFET structure being symmetrical about its gate axis, the source and drain terminals are interchangeably used. Using photolithography process in previously created gate layer, a high dose of dopants like phosphorus or arsenic is implanted and create source and drain. Similar processing steps, as described for NMOS fabrication, are employed to create PMOS transistor, source and drain regions. Compounds of silicon and titanium, cobalt or nickel-like metals are called silicide. They exhibit high electrical conductivity, thermal stability, and resistance to corrosion. By depositing silicide on the source, drain, and contacts, their resistance is further reduced and is known as salicide process. Commonly used P-type dopants or indium or boron are diffused or implanted at the predefined locations and create source and drain regions of P-type MOS transistor. Design is implemented by first creating pins of fabricated devices and then, as per design, establish connectivity. Once the devices are fabricated, the whole wafer is coated with insulating silicon dioxide layer. Contact cuts are etched, create cut openings in the dielectric layer and expose the underlying device pin regions. Using contact mask and etching process, contact holes are created by wet or dry etching process. Dry etching is a preferred process, as it creates an isotropic cut that has good side wall profile and shallow cut depth. As design complexity grows, the number of pins and nets increases exponentially. Functionality is realized by interconnecting the device pins. At cell level, metal 1 and poly layers are used to implement connectivity. However, poly, due to its high resistivity, is restricted to short nets only. The design routing is implemented by multiple isolated metals of varying width, along with vias establish interconnection. Net parasitic capacitance is optimized by routing alternate metal layers in the preferred direction. Metal routing is implemented by using photolithography, physical and chemical vapor deposition, planarization, and etching processes. Interconnects are classified as power and signal nets. Depending upon the design complexity, several isolated metal layers of varying width are employed. Generally, power nets carry high currents and are of higher cross-sectional area, offering lower resistance. This reduces net power dissipation and avoid metal electromigration phenomenon. Using physical vapor deposition process, metals net are deposited and the isolation layers are created by employing chemical vapor deposition process. Metals like aluminium or copper is deposited across the entire wafer. Interconnect mask identifies the nets needed. Using photolithography, the unwanted metal is etched away and establish connectivity. On completion of base and interconnect layer fabrication, I/O pins are created that enables signal and power connectivity. At cell level, in and output pins are passive metal bonding pads that establish electrical connectivity. At chip level, I/O cells are active cells that, in addition to establishing connectivity, perform functions like level shifting, noise elimination, signal reconditioning, buffering, etc. After completing the wafer processing, the I/O pins are created and the top surface is coated with silicon nitride passivation layer that protects the die from environmental and mechanical damages. Before further processing, the wafer containing multiple dice are cleaned and tested for functionality. The probe-tested dice are inked, scribed, and the rejected ones are weeded out. The sorted dice are mounted, wire bonded, and packaged. Using automatic testers, finished devices tested and sorted for selective parameters. Regular production batches are tested on statistical sampling basis and provide quality assurance. As per the customer requirements, batch-wise electrical, thermal, environmental and life tests are carried out and assure the product reliability. Figure shows the cross-sectional and top view of a process CMOS inverter cell. Cell top view displays the layout of base and interconnect layers in actual layer dimension form. The vertically sliced CMOS inverter cross-sectional view exhibits its internal layer built up. It displays the sequence of base and interconnect layers built up on the substrate. Wide range of functional logic cells are fabricated, characterized and optimized for area, power, and performance. Using this data, physical cell library is built, which also displays cell and frame views of the cells. The cell top view exhibits layer layout details. This layout view helps physical designer to perform the physical verification and ensure compliance of design layout to design rules. The frame view is an abstract view of a standard cell that displays pin locations, cell and routing boundary. Physical designer uses the frame view for placement and routing of the design. The primitive, only P or NMOS technology are associated with lots of limitations. The devices had higher threshold voltage, large leakage current, slower speed, higher voltage drop leading to higher power dissipation and temperature. These limitations are overcome by combined NMOS and PMOS transistors in the design, and is known as complementary MOS technology. A CMOS technology exhibits improved performance, lower power consumption, and higher noise immunity, but the structure is associated with latch-up issue. Twin well technology allows better control of the threshold voltage of both transistors, provides transistor isolation, reduces latch-up risk and enables use of higher supply voltages. SOI technology offers reduced parasitic capacitance, leading to faster switching speeds and lower power consumption, better isolation between devices and improved performance. A multi-die device involves integrating multiple semiconductor dies onto a single package and collectively implements complex functionality. Each technology has its own set of features and is selected based on the specific applicational requirement. Thanks for your time and hope this video has been helpful in appreciating the CMOS gate fabrication process steps involved and its related issues. Hope to meet you in upcoming video. Bye for now.